Talk about vectors in the plane. This is section 2.1 of the text. We're finished with chapter 1 and moving into chapter 2. We're going to talk about or be responsible for all of the goals at the start of section 2 here. Let's go look at that. So all of the learning objectives are on the table here for this particular lesson. We're going to talk about vectors. We want to be able to describe a plane vector using the correct notation. We want to be able to do basic vector operations. We want to understand how to express vectors in terms of their components. We want to be able to compute the magnitude of a vector and explain the formula for that magnitude. We want to be able to express a vector in terms of unit vectors. And finally, we want to familiarize ourselves with some examples of vector quantities and some applications of vector quantities. The big idea here, just to kind of put this all in context, we're in Calc 3 now. In Calc 1 and Calc 2, we were studying functions that essentially took a real number in as an input, as an independent variable, and produced a real number as an output, as a dependent variable. For example, y equals f of x, where f of x is x squared. So something like it might take a real number 2 and produce the real number 4, x squared. Vector calculus is a generalization of this idea of function, so that instead of receiving a single input number, a function might accept several input numbers. And instead of producing a single output number, it might produce several output numbers. Mathematicians over the years have discovered that the best way to represent a collection of input numbers is to just call it a vector. A vector is essentially a list of numbers. We're talking about vectors in the plane today where we have 2 numbers, but more generally it's a list of numbers, and we're going to be feeding that list of numbers into a function. And then depending on the kind of function, it might produce as output another list of numbers, which we'll also call a vector. This can be very general. We can have functions that take in a list of 2 numbers, a vector in the plane, and produces a list of 3 numbers, a vector in 3-dimensional space. We could have a function that receives a vector of 25 numbers in 25-dimensional space and produces a vector in 1-dimensional space, a single number, a scalar. And what we're trying to figure out here in this class, the entire class really is about, well, what kinds of ideas from Calculus 1 and Calculus 2 can be brought to bear on vectors and vector functions, and we'll discover that as we go through the semester. Now, we know the rules for working with real numbers. In fact, we're so comfortable with those rules that we might not even be aware that there are rules. We know how to add 2 real numbers. We know that, for example, real numbers multiplication distributes over addition. We know how to find inverses of real numbers. We know all kinds of things about real numbers. What we're going to do today is kind of lay the groundwork for what are some of the things that you can do with vectors. How do we add vectors? Can we add vectors? How do we multiply vectors? Can we even multiply vectors? So we'll talk about that. What are the rules of the game, right? You got to understand the rules of the things you're working with before you can start talking about functions, and certainly before you can talk about derivatives and integrals of those things. Real numbers, scalars as we call them, are single-dimensional quantities. They represent things like temperature, time, cost, profit. Vectors, on the other hand, can represent multi-dimensional quantities. These are quantities with magnitude and direction, and we're familiar perhaps with some of them from physics. Velocity is a vector. If something is moving in 3 dimensions, it'll have a velocity, and that velocity comprises a direction and a magnitude. The direction is where is it headed, and the magnitude is how quickly is it going there. Force. a similar thing from physics. But that's not the only thing. Really, any multidimensional quantity is well represented by vectors. Let's jump into the book briefly here and do a bit of a flyover of the section. And I want to kind of give you an intuition about vectors as just mathematical objects before we start slapping coordinates on them and thinking about them in terms of the Cartesian plane. So the definition of a vector here, it's a quantity that has both magnitude and direction. And by representation, really magnitude and direction, these are great abstract ideas, but humans kind of need metaphors, things to hang our hats on. And so the very first metaphor that we're going to use to represent a vector is the notion of an arrow in space. Let me draw an arrow in space for you here. I don't know, there's an arrow. Arrows are really good because arrows have direction and they have length. And because we're defining vectors to be quantities that have magnitude and direction, arrows are great metaphors for that because arrows naturally have a direction and a magnitude. So we'll be thinking about vectors in terms of arrows, and we will, just because it's nice to be able to talk about the anatomy of a vector, this is called the initial point. And the other end of the arrow is called the terminal point. That said, you're also going to encounter tail and head. And indeed, that's usually, those are usually the terms that I use. But the book likes initial point and terminal point. You'll see both. All right, so vectors are said to be equivalent if they have the same magnitude and direction. So if I take this vector and I make a copy of it and move it over here, these are equivalent vectors. They're equivalent because they have the same length and they point in the same direction. If I take this thing, you know, and I don't know, flip it around or move it, change its length or something like that, they're not equivalent anymore. Change its length or its direction, it's no longer equivalent. Okay. Now, sketching vectors, it's kind of hard to just think about vectors floating in space without anything to kind of sort of pin them down or identify them. It's great to draw a vector in a drawing program like this, but you know, how do we deal with these things mathematically? Often we will talk about vectors in terms of points. This notation right here, capital P or a capital letter followed by a coordinate pair, this represents a point in space relative to some kind of coordinate system. So for example, we might have a coordinate system like this, and the point 1, 1 is right here. You go out 1 in the x direction and you go up 1 in the y direction, and that's what this book is going to call P11. Q85, same thing, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5. There's Q85. These are points, they're not vectors, and there's a difference. Often you'll see this notation, ST with a bar on the top of it, and what this represents is the vector that goes from S to T. So here, the vector that goes from P to Q would be denoted PQ with an arrow on the top, and it would look like this. You would put the initial point of the vector down here at P and the terminal point of the vector up here at Q, and that's the vector PQ. So these coordinate pairs, these points, are ways of kind of defining vectors for us in a more rigorous way other than just drawing arrows on a sheet of paper. Okay, in contrast to vectors, as I discussed earlier, there are scalars. Scalars are just numbers. Think about real numbers like 2, 5, pi, e. Those are scalars. Vectors are these arrows. Arrows are not numbers, so they're different things. That said, we can define the product of a scalar and a vector by just defining this kind of multiplication. We say that a scalar times the vector essentially scales the length of the vector by k. If k equals 0, then you turn your vector into the 0 vector. If k is less than 0, you kind of reverse the direction of the vector. And if k is, say, 2, you're going to double the length of the vector, but it's going to preserve the direction. So the scalar k here, a real number, stretches and shrinks the vector, or might even change its direction depending on, it might point it in the opposite direction depending on its sign, but it will not change its direction other than just flipping it. So here are some examples. Here's the original vector v. Here's 2v, points in the same direction, but it's twice as long. Here's 1/2 v, same direction, half as long. And then here's minus v, same length, opposite direction. So that's scalar multiplication. Now, it really gets interesting when you start talking about adding vectors together. They have this beautiful geometric metaphor associated with addition. So let's go down a little bit more, give ourselves a little bit of space. You can think of a vector as sort of a set of instructions. So let's say I'm standing at the position of this little black dot, and let's say I want to tell the black dot to move in a particular way. And I say, I sort of draw this vector over here and I yell over to the dot. I say, hey dot, move like this. What's the dot going to do? The dot's going to move in this direction in this this length. So where does the dot end up after that? Let's see where it ends up by taking a copy of the instructions and putting the initial point on top of the dot. And what we see is the dot should end up right here. So after following those instructions, we can throw away the instructions because the dot has followed the instructions. And then what if you come along and you say, all right, well, dot, you've moved there, and now I want you to move here. What should the dot do? Well, let's take a copy of the instructions, put them over here, and the dot ends up right here. So if you imagine these vectors as sets of instructions, here's step 1, here's step 2. Step 1, step 2. A natural thing to do would be to say add the instructions together. So what does it mean to add these instructions together? Well, ideally what we would like is for when I add these two instructions together, I actually end up here. I skip right over step 1 and go straight to step 2. All right? Or not really step 2, but skip over step 1 and end up in the net location. Well, how do I figure that out? I can add these vectors together. So let's make a copy here, and let's make a copy of this guy here, and ask ourselves, what does it mean to add these two things together? And what it means is take this vector and take this vector and put them head to tail, like that. Then it becomes clear that the sum of these two vectors should be this green vector. All right, let me do that one more time. It becomes clear that the sum should be this green vector. All right, so the sum of these two vectors this vector and this vector is the green vector. And how do we figure that out? We put them head to tail. And see where we end up. Okay, that's the motivation for this diagram. Here's the first vector, here's the second vector, the red vector is the sum. And if you imagine that these are instructions for this dot, hey dot, move here, and then hey dot, move here, or you could say, hey dot, move v plus w, then the dot's just going to go here directly. All right, and that's, these two pictures just represent two different ways of looking at the same addition. Remember that vectors don't have position, they have length and magnitude. So whether I put this w here or whether I put it here, as in this picture, the sum is the same. Differences are similar. I won't belabor the point, but the difference between two vectors, v minus w, is the vector that goes from the tip of w to the tip of v if you place v and w tail to tail. Order matters in subtraction of vectors just like it matters in subtraction of real numbers. So if I look at w minus v, I get the same leg here, but the arrow points in the opposite direction. So I get a different vector, same length, pointing in the opposite direction. Alrighty. So here, the first example is just talking a little bit about the different operations that we've just learned. For example, 3 times w is just going to be w, same direction, 3 times longer. V plus w, take v and w, put them tail to tail, and look at the result. And then 2v minus w, you're going to take v, double its length, you're going to subtract w, and get the results. All of these should be done via sketches. Because after all, vectors are just magnitude and direction. They're very abstract quantities. Arrows are nice metaphors for that idea. That said, you can only go so far in mathematics with a metaphor, and you begin to need more quantitative representations. And so this leads us to the notion of components. Vectors can be well represented by components. But if you're going to work with components, you kind of have to assume a certain coordinate system. So we're going to define our vectors by placing their tails at the origin and giving the coordinate pair for the head or the terminal point. When you do that, the vector can then be called xy with these angle brackets around the outside as opposed to these rounded parentheses. Notation matters in mathematics, and this notation has a very specific meaning. It means a vector whose tail is at the origin, 0, 0, and whose head is at xy. Just a side note, these components, x and y, are scalars. This is a vector. These numbers are scalars. All right. If you have a vector with a generic initial point and a generic terminal point, you can express the vector in component form by taking the difference of the x coordinates and the y coordinates. So it matters where the initial point is and where the terminal point is. And this kind of goes back to, well, let's just do an example here. Express the vector with initial point -3, 4 and terminal point 1, 2. By definition, the vector is then 1 minus -3, aka 4, and 2 minus 4, which is -2. So this vector is going to be That was not helpful. This vector is going to be, there we are. So we sketch the vector and we compute v as 4, -2. And then if we wanted to plot it, we could put the tail at the origin and the head at 4 and -2. This is an equivalent vector, but it's not in sort of the standard location. So when we see notation like this, we immediately think about a vector situated thusly. Alrighty, let's keep rolling here. Beautiful thing about this component representation is lots of the vector operations that we've introduced in the abstract sense or using arrows can actually be done very explicitly, very mathematically using these coordinate representations. For example, scalar multiplication is as simple as distributing the scalar onto each component. So k times the vector is k times the first component, comma, k times the second component. Similarly, vector addition, it's so convenient for us, is really just the component-wise addition of the two vectors, x1 plus x2, comma, y1 plus y2. And this very simple calculation is perfectly equivalent to this arrow metaphor. Really, really handy. All right, magnitude of a vector. So we can do addition. We can also figure out the magnitude of a vector by taking the vector, building a right triangle, and using the Pythagorean theorem. The magnitude, after all, is just the length. So if you plot the vector with its tail at the origin and its head at xy, it's a straightforward geometric calculation using the Pythagorean theorem, x squared plus y squared square root, to get the magnitude. So that's why the magnitude is what it is. Here are a couple of examples asking you to compute these quantities using the component arithmetic that was just introduced. Theorem 2.1 sort of lays out all the things that you can do with vectors and sort of all the rules that they follow. For example, addition is commutative. U plus v is the same as v plus u. That's handy. There's a notion of distributive property. For example, scalar multiplication. Vector distributes over scalar addition. Scalar multiplication distributes over vector addition, and so forth. You'll very quickly start to take these rules for granted as we go forward, but each of them is a rule in and of itself and requires proof. Okay, trigonometry is a really important thing lurking in the background here. Let me go back to this right triangle representation. You have your vector here. You can always build this right triangle by putting the tail of the vector at the origin. So I can then immediately decompose this vector into two components. So let me grab a copy of this really briefly and show you what I'm talking about over in the notes. So you always have this geometric picture lurking, and you can turn these legs into vectors themselves. And what you notice is if you call this, say, vector u, and this side, say, vector v, then this side is u, vector u, plus vector v, like that. It's perfectly consistent with the arrow metaphor of addition that we introduced earlier. Well, what if you're given the vector, let's call it w. What if you're given the vector w? Can you figure out what u and v are? Well, you can if you can figure out its length and this angle theta. So if you know its length, and we actually have notation for the length of w, it's this double bar notation. That's the length of w, also known as the magnitude. And we can figure out theta by taking the arctan of y over x, and we can write the vector u, the horizontal component, is just going to be the length of w times the cosine of theta, which we could figure out from the arctan. And v is going to be the length of v times the sine of theta. These are called the components. These are called components of w. This is the horizontal, u is the horizontal, v is the vertical. So when you're asked, for example, find the component form of a vector with magnitude 4 that forms an angle of minus 45 degrees with the x-axis, you know, what are we talking about here? Well, we want a vector with magnitude 4. So let me grab some axes. And we want it to, so we're talking about magnitude 4 here, and we want it to go down minus 45 degrees. So something like in the vicinity of here, maybe. Oops. Something in the vicinity of perhaps here. I don't know why that's doing that. There we go. Minus 45 degrees. All right, how do we figure out what the components are? If we know that this length is 4, we're going to take 4 times the cosine of theta, which is minus 45 degrees. And that's going to be the x coordinate, and then the y coordinate is going to be 4 times the sine of minus 45 degrees. And we happen to know that the cosine of minus 45 degrees is root 2 over 2. And the sine of minus 45 degrees is minus root 2 over 2. And we'll simplify that as much as possible. 2 root 2 minus 2 root 2. And so this vector is angle brackets 2 root 2 minus 2 root 2. Now, just like we can figure out the magnitude of a vector, we can also kind of separate out the direction of a vector. The direction of a vector is a vector whose length is 1, kind of removing or normalizing out the length. And if you're given a vector v, you can find a vector that points in the same direction of length 1 by taking v and dividing by its magnitude. This we call normalization, and it produces a unit vector that points in the same direction as v. Now, when we have a vector like u pointing in this direction, pointing in the same direction as v, we say that it's parallel and that it points in the same direction. We can have another vector that points in the opposite direction. We would call that anti-parallel. It points in the opposite direction. So it's still parallel, but it points in the opposite direction. Okay, find the unit vector corresponding to 1, 2. Well, the first thing we have to do is compute the length of this vector. The length of 1, 2 is just 1 squared plus 2 squared, which is 5, and then take the square root. So the unit vector associated with v is just 1 over root 5 comma 2 over root 5. It's kind of annoying that every time I click on that it goes back to the top of the page, but oh well. There we go. Root 5 and then divide the vector by root 5. This is scalar multiplication by 1 over root 5 essentially. Okay, standard unit vectors, I, j, and k. I is, well, we don't have k because we're not in 3 dimensions. I is the vector 1, 0, j is the vector 0, 1, and you can always take a vector given x, y and break it up into x times I plus y times j. This can be convenient in some circumstances. So for example, this vector would be 3i minus 4j. I and j are recognized symbols for the standard unit normal vectors. Okay, let's get into some of the exercises here. I want to talk about exercise 10. Let's find the unit vector in the direction PR. Let's go back over to the notes here and make some space. Alrighty, so we know that P is at negative 1, 3, and R is at negative 3, 7, and we want to find, in number 10, the unit vector in the direction of PR. First thing we should do is compute PR, and we can compute this simply by subtracting coordinate-wise 7 minus 3 and negative 3 minus negative 1, and that yields the vector for negative 2. That's not a unit vector, or at least I don't think it's a unit vector. How can we confirm that? Let's compute the magnitude of PR. We take 4 squared plus negative 2 squared, square root. That is 16 plus 4 square root. That is 20 square root, aka 2 root 5. So that's definitely not 1. So this is not a unit vector. But we can make it a unit vector just by multiplying by 1 over 2 root 5 this vector for negative 2. I'm perfectly comfortable if you leave your answer like that. On the other hand, maybe in web work or in other contexts, you might be asked to distribute the scalar multiplication in onto the vector, in which case you get something like this. And then I would ask that you, in that situation, simplify it a bit. 2 over root 5 and negative 1 over 2 over root 5. And that's the unit vector that points in the direction of PR. Let's look at number 16. All right, in 16, for the given vectors, find the sum and express it in component form, and by using the standard unit normal vectors. A minus B, verify that A, B, A plus B respectively satisfy the triangle inequality, and determine these various quantities. So why don't we grab a copy of all of those instructions for our notes. And then let's grab a copy of number 16 here. And let's do all the things. So determine the vector sum and express it in both the component form and by using the standard unit vectors. All right. In component form, first let's write A as a component form. So that's 2i, 0j, and B is just negative 2 in the x slot and 2 in the y slot. Now if you were going to add these two, you can just add component-wise. So 2 plus -2 is 0, and 0 plus 2 is 2. And then if you want to write that in using ij notation, that's 0 times I plus 2 times j, which just simplifies to 2 times j. So that's part A of this exercise. Let's continue on here. Part B, find the difference and express it in component form. All right, so for the difference, A minus B, again, we have the advantage now of having computed the component form. So we can look at 2 minus -2, which is 4, and 0 minus 2, which is -2. Make sure you always go in the same order, A minus B, A minus B. All right, and in component form, this is just 4I minus 2j. All right, verify that the vectors a, b, a plus b, a minus b satisfy the triangle inequality. This is really an exercise in computing some magnitudes. Let's find the magnitude of A. A is 2, 0, so the magnitude of that is going to be 2. The magnitude of B is going to be 2 squared plus 2 squared is 8. Square root, that's going to be 2 root 2. And then finally the magnitude of A plus B is going to be 2. Now if things are working properly, we should have, from the triangle inequality, we should have that the magnitude of A plus B is less than or equal to the magnitude of A plus the magnitude of B. So let's see if that's indeed the case. We see that the magnitude of A plus B is 2, the magnitude of A is 2, and the magnitude of B is 2 root 2, and that's certainly true. This is true, so the triangle inequality gets a big check mark. I'll let you figure out the A minus B part of that one. For part D, determine the vectors 2A minus B, 2A minus B. All right, so part D, let's find 2A. This is the scalar multiplication of 2 by A. You distribute 2 onto each component of A and you get 4, 0. Negative B, this can be thought of as the scalar multiplication of -1 onto B, and so that yields 2, -2. And finally, 2A minus B is really just a matter of adding these two together. 2A minus B, just add component-wise. 4 plus 2 is 6. 0 plus -2 is -2. And then we can express this in ij form or standard vector form as 6I minus 2j. All right, let's talk about problem 21. In problem 21, we've got, this is a twist. We've got a vector that's made up of functions. That's certainly a thing that we can do now. So we have this vector function, and this vector A, that's a function of t. Write the vectors a0 and a pi in component form. What does that mean? Really, it's just a matter of plugging in a for t, 0 for t, and pi for t. So a of 0 is plug t equals 0 in here, cosine of 0 is 1, sine of 0 is 0, and so a of 0 is 1, 0. What's a of pi? Plug pi in for t, cosine of pi is -1, sine of pi is 0. That's part A. Part B. Show that the magnitude of this vector remains constant for any real number. So the magnitude of A of t is the square root of the first coordinate squared plus the second coordinate squared, square root. Of course, we know that cosine squared plus sine squared is 1, and that the square root of 1 is 1. And so we do, in fact, see that this does not depend on t. What about C? As t varies, show that the terminal point of the vector A describes a circle centered at the origin of radius 1. I don't know that there's a whole lot to show here. We recognize that x of t equals cosine of t, y of t equals sine of t is a parameterization of the unit circle. And since that's where the terminal point is, we can safely conclude that the terminal point does in fact trace out a circle. Let's look at 45. Make some space here. So annoying that that keeps going to the bottom there. I have to figure that out. The speed of an object is the magnitude of its related velocity vector. All right, that's an important definition. Speed is the magnitude of the velocity vector. And we have a football thrown with an initial speed of 70 miles an hour and an angle of elevation of 30 degrees. Determine the velocity vector in miles per hour. Alrighty. So what do we know about the magnitude of this vector? Let's name this vector A. We know that the magnitude of A is 70. Can we find a vector that points in this direction 30 degrees above horizontal? Well, in fact, we can. We can actually find a unit vector based on this earlier work about cosine t sine t. We can look at cosine of 30 degrees sine 30 degrees. This vector points in the direction that we desire. Remember that 30 degrees is pi over 6, and the cosine of pi over 6 is just root 3 over 2. And the sine of pi over 6 is 1/2. So we can actually determine the vector now by computing 70 times root 3 over 2, comma 1/2. And that is 35 root 3, 1. How did that 70 turn into a 35? I factored the 1/2 that was in both components out front and simplified. So this is the velocity vector of the football. All right, one more. Problem 59. Okay. A guy wire supports a pole that is 75 feet high. One end of the wire is attached to the top of the pole, the other is on the ground 50 feet from the base. We want to determine the horizontal and vertical components of the force of the tension in the wire if its magnitude is 50 pounds. So we know the magnitude of this vector right here. The magnitude is going to be, let's call this vector A. The magnitude of A is just 50 pounds. That's the tension in this wire. We know that, for example, if the angle down here that the guy wire makes with the ground is theta, then the horizontal component is going to be, let's call it x, since that seems like a reasonable label for it, is going to be 50 times the cosine of theta, and the vertical component is going to be 50 times the sine of theta, like that. What is the cosine of theta? What is the sine of theta? Well, we know that the sides are 75 and 50. We can find the third side, because this is a right triangle, using the Pythagorean theorem. And in fact, I'm not going to bother with this guy. I'm going to work with a simpler triangle where this side is 2 and this side is 3. In that case, the fourth side, or the third side, excuse me, is the square root of 13. And then the cosine of that angle is the opposite over the hypotenuse. Sorry, the adjacent over the hypotenuse. So that's 50. Adjacent is 2, hypotenuse is root 13. 50 times 2 over root 13. And the sine is going to be 50. The y is going to be 50 times the sine of theta, 50 times 2/3. And so the horizontal and vertical components of the force are 50 times 2 over root 13 horizontal, and 50 times 2/3 for vertical. All right. So to get familiar with these concepts, I want you to work on as many of the exercises 1 through 60 as you feel you need to. And when you finish that, go ahead and take the web work assessment for Chapter 2, Section 1. Thanks.